Hello dear students, welcome to my YouTube channel. In this video I am going to give list of formulae from the chapter moving charges and magnetism. In the previous videos also I have given list of formulae for few chapters, and here I am going to give list of formulae for this chapter. Okay, so if you have already studied the theory concepts, derivations and all, these concepts will be very easy for you to understand. Then nothing else, just take pen and paper, write down all the formulae and practice them, so they are very important. So let's start. So first of all we have Biot-Savart's law. Biot-Savart's law. So here if we consider a conductor, okay, like this is a conductor, so which is carrying current how much? I ampere. Okay, so when a conductor carries current, it produces magnetic field around it. So at this particular point P, which is at a distance R, okay, so what is the magnetic field produced? So instead of considering the full conductor, I am going to consider only small current element, that is dl. So if you write I dl, that will become current element. So this is the length element dl, okay, which carries current I. Then magnetic field is produced due to this current element is given by dB is equal to I dl sin theta divided by r square. And if you remove this proportional sign, you will get a constant, so that is mu naught by 4 pi I dl sin theta divided by r square. So this is the magnitude. I can write this in vector form, that also we have already studied, that is dB is equal to mu naught by 4 pi I dl cross r divided by r cube. Based on this you can see two CET questions, direct questions, like finding the actual form of Biot-Savart's law. Okay, based on this formula they have asked twice. And then we have one more formula, that is Biot-Savart's law in terms of velocity and charge. Dear students, we have already studied what is current. Current is net flow of charge, right? So net flow of charge, so we can write it as I is equal to Q by T. I is equal to Q by T. So here if you substitute I is equal to Q by T, you will get Q divided by T. Q will be there as it is. Q will be there as it is. This distance by time taken, whatever is there, let me show you. Here Q by T is there, right? So this distance divided by time, that we can write it as velocity. So distance traveled by the charge there per given time, that is velocity. So by converting that, by substituting I, we get this formula dB is equal to mu naught by 4 pi Q into V cross R divided by R cube. Okay, so this is very important. Once they have asked a question on this one also. Now let us move on to the next formula. So this is next thing that we need to consider here. We are considering a straight conductor, okay, of infinite length or finite length. So what is the magnetic field produced at this particular point P due to this one? So let me read this. So if a conductor of finite length carries a current, the magnetic field at any point near it is given by. So how to calculate it? So let us consider this and draw these lines like this, so which makes an angle alpha and beta here, or theta 1 theta 2 here. Okay, so from that we get this formula B is equal to mu naught by 4 pi r sin alpha plus sin beta. So sin alpha plus sin beta, or if you want to write theta 1 theta 2, you have to write cos theta 1 plus cos theta 2. If you take these angles, sin theta, if you take these angles, cos theta. So that is all about this formula. Write down, this is also very important one. Okay, so next, the same case if you consider this point at any one end of this wire, okay, infinite wire. So if you consider here, theta 1 will become infinity, or alpha will become, theta 1 will become 90 degree, or alpha will become 90 degree, and other angle will become 0. So if this becomes 90, this will become 0. If this will become 0, this will become 90 degree. Same thing happens here also. So one angle will become 90 degree and other angle becomes 0. So this will go off, one will become 0 and another will become 1. So we don't write these angles at all. So what will we get? Let me take here. So if the point P is near one end of an infinitely long wire at a perpendicular distance, then alpha 90 degree, beta is 0, or theta 1 is 90 degree, theta 2 is 0, or vice versa. So then this will become mu naught I divided by 4 pi r. Here mu naught I divided by 4 pi r into this one is there, this will become 1. So we write only this part, mu naught I divided by 4 pi r. Okay, next we have case 2. If the wire is of finite length and the point is at a perpendicular distance, exactly perpendicular distance if it is there, then alpha will become beta, right? So if it is exactly at the perpendicular distance and especially perpendicular to its middle point of the conductor, then alpha value and beta value will become same, and theta 1 value, theta 2 value will become same. So you can write 2 times of alpha or 2 times of beta, right? So or 2 times of theta 1 and 2 times of theta 2, like that. So you will get this 2 mu naught I divided by 4 pi r into 2 sin theta. Okay, then we have Ampere circuit law. So line integral of magnetic field around a a straight conductor carrying current is equal to mu naught times current enclosed by that path. Okay na? So for previous year students, this question was given in the board examination. Then if you solve that for a straight conductor, you will get Bu is equal to mu naught I divided by 2 pi r. Okay, next, this is famous derivation. I have just written the final formula here. Magnetic field due to circular coil carrying current, based on this in previous year's question papers. So there was somewhere around 3 to 4 questions, maybe 5 also. So there were many questions that you can see that were given in previous year question papers. Very important one. So for that you will get this formula. What is that? B is equal to mu naught by 4 pi 2 pi I n r square divided by r square plus x square power 3 by 2. And if x value becomes 0, where when if you consider the point at the center, x value will become 0. If you bring this point this side, okay, at the exact center, then x value will become 0. So at the center, then if you solve this, you will get this. Take 0 at x, remaining you can solve. So you get this. Next we have, if the conductor is bent into like an arc, okay, magnetic field at the center of the current carrying circular arc. Okay, see, if you have a circle like this, magnetic field is this one. If we consider only part of that circle, okay, this much only if you consider, okay, this much only if you consider, you have to consider this angle theta. So how much is that? So theta, but that should be in radians. So divided by 2 pi radians. Okay, so that's why we have to divide it by 2 pi. Okay, so we get this formula for that. Arc, magnetic field due to circular arc. Then we have the solenoid. Magnetic field at the axis of the solenoid or inside the solenoid along its axis is given by mu naught Ni divided by 2. This is for finite length. If you have finite length, you have to take sin theta 1 plus sin theta 2 as we have considered for a conductor, mu naught Ni divided by 2. Then if you consider infinite length solenoid, see, solenoid looks like this. If you consider a solenoid of infinite length, then magnetic field become mu naught Ni. There is one more case here. If you consider the magnetic field at any one point of infinite length solenoid, then you have to divide that mu naught Ni divided by 2. You will get divided by 2 if you consider the what is that, the point at any one end of the solenoid. Okay, so the magnetic field lines produced inside the solenoid are represented like this. Inside the solenoid, the magnetic field lines are parallel, so uniform magnetic field lines will be there. Outside, magnetic field lines will vary, so actually total magnetic will become 0 outside the solenoid, so we don't consider that. Then next we have magnetic field due to finite current sheet is B is equal to mu naught K divided by 2, where K is called linear current density. We have studied about linear charge density, so that is L. Here we have considered linear current density. So then we have some special cases where, see here we have a circular current carrying conductor which is carrying current in this direction, like we can consider anti-clockwise direction, and there is one more wire here which is carrying current from left to right. Okay, so at the center of the loop O, for the straight wire and the loop arrangement, what is the magnetic field? What is the magnetic field at this particular point? So here there is a conductor carrying current I, also there is a conductor like this carrying current I. Due to both of them, the magnetic field produced is B is equal to mu naught I divided by 2R 1 plus 1 by pi. Okay, if in case, if the loop carries current like this in clockwise direction, and this one is carrying current in this direction, so this current inside the loop is opposite to this current, so that's why the magnetic field produced is similar to this one, but here we get minus sign. Okay, so write down this formula. This is also very important, but in CET they have not given questions on this, much questions on this. Okay, so next one, if there is a semicircle, so due to this one and this one, at this particular point magnetic field will be 0 because it is along the axis of the conductor, magnetic field will be 0. Straight conductor, magnetic field will be 0, but if you consider on either sides, magnetic field will be there, so you just have to consider this one. Okay, so you can apply the formula that I have given earlier also, that is mu naught I divided by 4 pi r sin theta 1 and sin theta 2. This is for circular loop, right? Let me consider circular loop. So here it is, for circular loop it is mu naught Ni divided by 2r, mu naught Ni divided by 2r. If you consider a arc, semicircle like that, you have to multiply it by angle. So let me consider mu naught Ni by 2r, right? Let me substitute that here. So what do you get? B is equal to mu naught N is 1 I divided by 2r into theta. Theta is how much here? 180 degree, means pi divided by 2 pi. So pi will cancel out. 2 2 is a 4. You will get the same thing. Okay, so you can make use of the formula and derive this. Next, toroid. See, magnetic field inside the toroid is mu naught Ni. This is also very important. Then this concept is very important, the one I am going to give now. Force on a moving charge. See, if the charge moves inside the electric field, it experiences force. Okay, what if the charge moves inside magnetic field? Then also it experiences force. But there are some cases here. If you place a charge in electric field, whether it is moving or not, it experiences force. But in case of magnetic field, it is not like that. It should move with some angle, particular angle. So magnetic field is in this direction, charge is moving in this direction, then it experiences forces. In other cases, it may not experience force, or it may experience minimum force. So here F is equal to QVB sin theta. F is equal to QVB sin theta. So that you already know. Here the Q is charge moving with velocity V in this particular direction, making an angle theta with the magnetic field. Then force experienced by it is given by this, and direction of force, you can make use of Lorentz force formula. Or see, if this is the direction of force, this is the direction of magnetic field, force will be perpendicular to it. Okay, so Fleming's left hand rule you can make use to find the direction of force here. Okay, then if in case the sin theta values varies, if theta is 0 degree or 180 degree, means if charge particle is moving parallel to magnetic field, the force experienced by it is 0. And if in case, if the velocity of charge particle is 0, means charge is at rest. Charge is at rest means velocity is 0 inside the magnetic field. Even though the charge is present inside the magnetic field, it will not experience any force. But in case of electric field, it experiences force. Q, whether it is moving or not, in electric field it experiences force, but in case of magnetic field, it will not experience force until and unless it moves with velocity V, making an angle theta. Next, if the charged particle enters the magnetic field at an angle 90 degree, means magnetic field is in this direction, charged particle enters like this. So velocity of the charged particle is in this direction, magnetic field is in this direction, perpendicular angle will be 90 degree. Then it gets trapped in the magnetic field. Okay, so here I have given the direction of magnetic field is into the plane of the board. I hope you have already studied these basic things. This is represented by represented for magnetic field into the plane of the board. If magnetic field is out of the plane of the board, it is represented like this. Okay, so into like this, out like by using a dot. Okay, now the charged particle tries to enter this and get trapped inside the magnetic field, and it moves in circular path of radius how much? R. Okay, so then it experiences centripetal force given by Coulomb's force. Now by using that, centripetal force is given by mv square by r, that is equal to so not Coulomb's force, it is force which is given by this one QVB sin theta. So here QVB sin theta is 90 degree. Okay, sin 90 is 1. Okay, why? Because it has entered the magnetic field at an angle 90 degree. So QVB. Next we have velocity of charged particle in circular path. Velocity, how much is that? Just take this velocity cancel out, one more velocity will be there, QB divided by R, QB into R divided by M. Okay, that is the answer for this. Next, V is equal to QBR divided by M. Then if you want to calculate the time period, so we already know velocity is equal to distance by time taken or displacement by time taken. What about time taken? Displacement by velocity. Displacement by velocity. Let us take velocity this side, time this side. You will get time is equal to velocity by displacement by velocity. So here, if you consider the charged particle is covering a displacement or a distance of how much is that? Circumference. So the circumference is called what? 2 pi r. So 2 pi r divided by velocity, displacement by velocity. So 2 pi r value is substituted here, r by v value. So if you take r and v one side, so r by v value is m divided by qb. So just substitute that, you will get this. So time period of electron or charged particle trapped inside the magnetic field revolving in circular path, and its frequency is given by 1 by t. We have t here. Let us just take the reciprocal of that. Then we have angular frequency omega is equal to 2 pi f, that is equal to 2 pi f value qb by 2 pi m. 2 pi will cancel, it will get qb by m. Then we have kinetic energy of the charged particle moving inside the magnetic field in circular path. So that is half mv square is equal to qbr divided by 2m whole square. Okay, this is all about this one. If the charged particle moves perpendicular to or enters perpendicular to magnetic field, this is the second case in this. Okay, if it moves with some angle, then it moves in different direction, or it may get into helical path also, or any other path like that. Okay, we'll show that direction of the motion of the charged particle. So there will be constant force acting on the charged particle moving in magnetic field, and its direction will be keeping on changing. Okay, so if you understand this concept in depth, so the concept is very interesting. Okay, so as otherwise let me just give formula for this, because this video is mainly made to make the list of all the formulae. Okay, for understanding the concepts we'll make a few other videos. Okay, now as of now, next, if the charged particle enters the magnetic field with an angle theta whose value is not equal to 0, not equal to 90 degree, not equal to 180 degree, then the path traced by the particle will be helical. This is very important. So that is given by this. I think we have already studied what is pitch, right? This is called pitch, the horizontal distance covered by the charged particle in this particular helical path. Okay, this is all about this. Okay, charged particle, when charged particle enters magnetic field, there are three cases. One is this, second one is perpendicular, and the third one is not perpendicular, not parallel. Okay, next, a new case. This is 5 marks derivation for board examinations. Okay, I have just given the final formula. Force between two parallel conductors carrying current. Okay, now if the two conductors carrying current in the same direction, then force will be in the same direction, or means force will be attractive. They are in opposite direction, they attract each other. Okay, that is very important. Based on this, you may expect questions in KCET or NEET. Okay, the nature of force is attractive if the direction of current is same. If the direction of current is opposite, let me consider this is carrying current I1, this is carrying current I2, then the nature of force between those two is repulsive. Okay, this is calculated or found by using Fleming's left hand rule. Okay, then force is given by F is equal to F1 is equal to F2 is equal to mu naught by 2 4 pi 2 I1 I2 divided by d square into L. Based on this also, maybe as I have observed, there were like 4 to 5 questions given in KCET as well as NEET. Very important concept to practice this formula. I hope you have already studied this for board examination, and now it will be easy for you to understand, and it should be like a revision for you people. Okay, next, torque on a current loop in magnetic field, it is given by tau is equal to m cross b. Tau is equal to m cross b, where m is called magnetic dipole moment, which is placed in magnetic field B. Magnetic dipole moment, it is given by I into A, or if number of turns are n into I into A. Do remember that. Next, we have moving coil galvanometer. When it is placed in varying current, so we can see the deflection. So it is measured to sense the or find the presence of current in the conductor. So current passing through the conductor or coil is directly proportional to the deflection here. So if current is there will be deflection. So current is directly proportional to deflection. If no current, no deflection at all. So that is given by this one. N means number of turns in the coil, I current passing through it, area of cross section, B is called magnetic field. That is equal to C into theta, where C is called couple per unit twist, K is called galvanometer constant. Okay, then theta by I current sensitivity, theta by T is called current sensitivity. From the same formula it is derived here. Okay, theta by T, if you take, T will come this side, so BAN divided by C. Next we have voltage sensitivity, theta by V, that is equal to theta divided by Ig, where G is called galvanometer resistance, not galvanometer, it is galvanometer resistance, or you can write RG also if you get confused. So no, it is galvanometer resistance. Then we have, so let us take this I to the numerator, so we'll get this. So theta divided by V is called voltage sensitivity, theta by I is called current sensitivity. This is galvanometer resistance. Galvanometer resistance, let me write resistance of the galvanometer G. Okay, so this is all about what is that, moving coil galvanometer. Next, conversion of galvanometer into voltmeter and conversion of galvanometer into ammeter. First we have ammeter thing. So for converting the galvanometer into ammeter, we have to connect a shunt resistance or low resistance in parallel. I think this was given in board examination for 3 marks. Okay, so here since these two are connected in parallel, so in parallel combination, what is same? Potential is same. So V is equal to IR. Okay, IR, R is here G. Okay, galvanometer resistance, or if you want you can write RG also, galvanometer resistance. Here I have just written G, that is equal to current into resistance here, that is I minus Ig into S, shunt resistance. Next we have conversion of galvanometer into voltmeter. Here you have to connect high resistance in parallel with the galvanometer. So that is here in high resistance in series with the galvanometer. So here voltage, total voltage is given by voltage across galvanometer plus voltage across resistance. So V is equal to Vg plus Vr. V is equal to Vg is given by IR, right? So Ig into G. G is called galvanometer resistance. Then same current flows through resistance also, since it is in series. So what is this? Same current flows through Rg. So Ig into G. Okay, then R is equal to V by Ig minus G. So this is all about this video, dear students. We'll meet you in the next video. Till then, take care. Bye bye. One more thing, don't forget to share and subscribe. Thank you.